everyone, and welcome to part one of our lecture on chapter 5, Measurement Concepts. To start our conversation on measurement concepts, we really have to talk about scales of measurement. Scales of measurement are different in the ways that we measure constructs in the assessment process. So, a lot of times, there are different ways that we need to measure a construct, and we use different types of scales to match the specific construct that we are measuring. So, typically, there are four scaling methods: nominal, ordinal, interval, and ratio that increase in their complexity to measure various constructs in counseling. There are three characteristics of which these scales may possess a combination. So one of them is magnitude, the other is equal intervals, and the third is absolute zero. The more characteristics for a particular scale of measurement, the more complex information will be gained about that particular construct. So, as your scales get more complex, you incorporate more of these characteristics. So, magnitude, equal intervals, and absolute zero. And the more of those you have, the more complex information you are going to gain about your particular construct. So, let's go into a little bit more detail about each one of these. A nominal scale is a scale that does not possess any of the three characteristics of scales of measurement. They don't include magnitude, absolute zero, or equal intervals. And nominal scales are really only used to name or classify items or levels of a particular construct. So examples might be race, ethnicity, political affiliation, things like that, where you're classifying. And this is the most basic of the measurement scales. Groups in a nominal scale, or the classifications, are no greater than one another. And any number that you assign to each group or each classification is really actually pretty meaningless. So you might say everyone who says that they are Republican is 2, and everyone who says that they're Democratic is a 1. Those numbers don't mean anything because you're not saying that the groups are better or worse in any way by their number, but rather you're just classifying your participants through them. So that's a nominal scale. We also have an ordinal scale, and an ordinal scale possesses a magnitude characteristic. So, specifically, as counselors, we're able to note for a construct whether an item or a level represents having more or less relative to the other items or levels within that construct. So, a really important and really common example that we have is Likert type scales. And a Likert scale is usually from 1 to 5, where 1 means not at all like me, and 5 means the most like me, and 3 means not at all, or like somewhere in the middle, and then you have 2 and 4 that are intermediate steps. You can say that this is an ordinal type scale because you can say where someone falls in relation to the other options that are available. So there's a magnitude that can rank them to one another. But these intervals in the space between each value is not equal. So we don't have an equal interval. So a good way of thinking about this is that the difference between 1 and 2 on a Likert scale is likely different from the difference between 5 and 6 on that same scale. They might mean different things. So the numbers aren't perfect. They're not equal from one another, but we do get this magnitude piece that's added in an ordinal scale. With interval scales, we are providing information about both magnitude and equal intervals. So ranked items on an interval scale, or the levels within an interval scale of a construct, are of equal length and spacing from one another. But the one thing that is missing is that they don't have an absolute zero on intervals. So some examples of interval scales might include things like temperature, checklist of behaviors, and standard deviation. So when we say that these interval scales are lacking an absolute zero, what we're saying is that if you give someone a 0 on this particular scale, it doesn't mean that there's a complete absence of that thing. There's no such thing as the absence of temperature or the absence of behavior. or the absence of a standard deviation. Rather, the zero means something and it's just not absolute. And then our most complex scale of measurement is a ratio scale, which possesses all three levels of measurement: magnitude, equal intervals, and absolute zeros. Ratio scales are rarely used in the counseling assessment field just because it's really hard to get something that has an absolute zero. So, some examples might include things like time and height, where you can have zero time. There's an absence of time on an interval, or you can have the absence of height on something. And all of these scales of measurement really lead us into a conversation on reliability within assessment. So, reliability refers to the degree of consistency with each construct that is measured in an assessment. And this consistency can be evaluated across the same or similar assessments within the same assessment, or even across raters. And it is not an estimate related to scores of a particular sample. Or, sorry, it is an estimate related to the scores of a particular sample and not the assessment itself. So, there are some synonyms for reliability that you might see in research, and those are dependability, reproducibility, instability, and consistency. And there are three main concepts, or three key concepts, that are related to reliability that we're going to talk about in more detail. So those include measurement error, correlation, and coefficient of determination. And we're going to break down each of these, but I want to highlight that reliability, again, is an estimate related to the scores of a particular sample that we are assessing, and not about the assessment itself. So if we go into a little bit more detail on measurement error is the positive or negative bias within an observed score. So what that means is that a score that a person receives on a test is made up of two components or two elements: the person's true score and some error score that can either add to or subtract to their true score. Within assessment, a true score can never be known because greater error results in more inconsistency across scores. Measurement errors should be minimized. So we never know a true score on an assessment. A true score would be what we are actually measuring when we say someone's happiness. Like, their true happiness can never be fully captured. We just have an approximation of how we try to measure happiness through various scales. But within true scores, we have these measurement errors that can sometimes lead to inconsistencies in someone's true score. And because we don't want that to influence our true score too much, the goal of assessment then becomes trying to reduce or minimize any measurement errors. A test with perfect reliability would equate to no measurement error. And this situation is actually impossible because error originates from the individual, from the test that you're using, and from the testing conditions. Individual error might include things like whether or not your participant has some test anxiety, if they are interested in responding in a socially desirable manner, so they're changing their answers to what they think you want to hear. It can also include if they're familiar with the test. All of that would contribute to our individual error. Test error might be found if not all of the symptoms of a construct are adequately represented in our instrument, or if our test length is not ideal, so it's too short or it's too long. All of those can go into testing error. And then we also have testing condition error, which can refer to different scoring errors that you might engage in as the assessor. It can also include distractions in the environment, or insufficient administration time, or a noisy agency. So if you have someone who's taking an assessment and you are supposed to give them 3 minutes to complete a task and you only give them 2, that's an error in the testing condition. We talk about measurement error as being part of the equation concerning reliability. So there's a specific formula that we have with reliability that is said to be related to our observed score. So our observed score X is some combination of our true score T and our error score E. And any attempts that we have to maintain the uniformity of testing conditions by controlling our instructions, following proper time limits, and the testing environment are all undertaken in an attempt to reduce any measurement error variance that could occur and to make our tests more reliable. So if we can reduce measurement error, we can increase the reliability of our samples. The second of the concepts that I want to talk about in relation to reliability is correlation. And the correlation coefficient is an example of a reliability estimate, especially as it measures the relationship between two sets of measures. Correlation coefficients can also show what proportion of an observed score is assumed to be the true score, which is how it relates to reliability. So within correlation coefficients can range anywhere from 0 to 1, with stronger coefficients represented by larger numbers. But each of your correlations can also have a positive or negative valence, so they can change in direction, in the sense that a negative correlation coefficient relates to a negative relationship between two items or two measurements, and a positive relationship means that they move in the same direction. So for a positive correlation, as one item increases, the other increases. For a negative correlation, as one item increases, the other decreases. So we have a couple of examples. So you might have something that says plus 0.87. This is a pretty strong correlation because it's close to 1, which represents a perfect correlation. And this is a positive correlation. So as one item increases, the other increases. A correlation of 0.04, on the other hand, is a pretty weak correlation. Because this correlation is closer to 0, and 0 represents the absence of a relationship between these two concepts that you're interested in. And then you might have something like negative 0.15, which is a minimal correlation. These items are somewhat related to each other, but they're in inverse relationships. So as one increases, the other decreases. The Pearson model moment correlation coefficient is the most commonly used correlation coefficient. You've probably seen it in research. It's the one represented by a lowercase r. When we are looking at correlation coefficients, sometimes it's helpful to plot these values in a scatter plot so that you can see how the correlations work together, and you can see how higher values depict more of a linear relationship between two variables. So as you'll see in the first sort of upper left image here, this is a correlation of 0.8. So they're pretty consistent. As one increases, the other increases, and you can tell that by how close together the points are to one another. They're following pretty much the same trajectory from bottom left to top right. If you inverse that relationship and you make it a negative 0.08, as you can see in this second image, this is going to be a negative correlation where they're going to move in the opposite directions. As one value increases, the other decreases. And then a relationship that has no, or a correlation that has no coefficient, it's a complete 0, your scatter plot is going to look like this bottom left. It's going to be all over the place. There's no relationship between the variables. And then the bottom right is a perfect correlation. So a perfect correlation of 1.0, where all of the data points fall in the exact expected line. Within the assessment of reliability with using correlation coefficients, it's important to talk about how these relate to our true score and our observed score. So our observed score is made up of our true and our error scores. So, reliability then is an estimate that expresses the relationship between our true and our observed scores. And you can see it in this formula here, where our true score divided by our observed score, which is our true score plus our error score, when you talk about those in relation to one another, it creates our correlation coefficient of reliability, our R. And in essence, each half of the fraction is conceptualized as a variable, and then they are then correlated to each other. So the reliability then becomes the relationship of one score with another actual or hypothetical test of that score. So an acceptable reliability estimates typically range um, will typically depend on the type of test that you're administering, but tend to range between zero point 0.7 and 0.95. High stakes tests tend to have reliability estimates that are around zero point 0.9, whereas some personality measures may have estimates that are in zero point 0.7 or zero point 0.8 range. And reliability is actually a property of the test scores for a particular group on whichever sample you are administering your assessment. It's not of the test itself. So, reliability scores are sensitive to the size and type of sample or type of people because smaller and more homogeneous groups are going to introduce more error. So, the more similar to one another your participants are, or the smaller your group, the more error you're going to have and the lower your reliability is going to be. Also, a substantial correlation between two variables does not imply that either variable causes the other. They can both be under the influence of some third variable, or maybe even the relationship can be flipped. Because, as you probably remember from your undergrad days, correlation does not indicate causation. And then the third concept that I want to talk to you all about in relation to reliability is the coefficient of determination. The coefficient of determination is the way that we are trying to explain any shared variance between two variables. So, how two variables are related to each other and the information that we can have about that shared relationship. And the correlation or the coefficient of determination is calculated by squaring the correlation coefficient that we just established. So this estimate can provide information regarding the amount of shared variance between two sets of measures. With higher correlations, there's greater variance explained or greater shared variance. So if you have a correlation of 0.8 and you square that, you end up with a shared variance of 64%. So your coefficient of determination is saying if you have two variables that are correlated at 0.8, based on this formula of squaring the correlation coefficient, you can say that there's a 64% shared variance between those two variables. So those two variables are similar on 64% of what we would expect for the relationship at 0.8. So this is sort of like how we calculate reliability. But there are also types of reliability. And some of these you may have heard about because there are several different ways that we can measure reliability. And what that means is that there's no single measure of reliability for a test or a set of test scores, but rather we can use different types of reliability and get different reliability coefficients depending on how we are determining our reliability. So there are some major types of reliability. They include test, retest, alternate forms or parallel forms, internal consistency, which includes split half reliability and inter-item consistency, and we also have inter-rater reliability. And we're going to break down what each of these are in more detail, but I also wanted to let you know that if you're having a hard time distinguishing these types of reliability from one another, Table 5.2 in our textbook is a really great breakdown of each method that can help you just keep them organized if the way that I introduce it might be a little bit confusing. So make sure that you're using that resource if it's helpful. So the first of these types of reliability is test-retest reliability. And test-retest reliability really evaluates consistency across identical tests. So when you are using test retest reliability, you have the same test takers take the same test twice. So they take the exact same test, it's the exact same people. You have them take it at time 1, and then you wait a little bit, and then you have them take it at time 2. And you look for the reliability in their scores from time 1 to time 2. It's really important to evaluate that test retest correlations will tend to decrease as the interval or the amount of time between your test administration lengthens. So, if from time 1 to time 2 you have years of time, reliability on test retest reliability is going to decrease. If the interval is too brief, though, there are potential practice and memory effects, which can tend to make your reliability estimation spuriously high. So if you only give people 10 minutes between testing intervals, they're probably going to remember their answers and their reliability is going to be higher, but it could be due to the fact that they've been exposed to the test before. Also, if your interval is too long, you can suffer from maturation and history effects, which can make your reliability spuriously lower than what you would expect. So people just forget over time, or they age and they have just moved on. The second type of reliability is what we call alternate forms reliability, which is an estimate across equivalent or parallel forms of an assessment. Sometimes we call alternate forms reliability parallel forms reliability. And because, actually, the way that you have this work is that you give two equivalent alternate forms of the same assessment. So they're parallel forms to one another, but they're different. So you have test A and test B. They're all measuring the exact same thing, but they are technically different tests because they're asking the questions in different ways. So the way that you establish reliability and alternate forms reliability is by having the same group of individuals take both tests. Because the items are different, the effective memory and other carryover effects that we talked about in test retest reliability are eliminated in alternate forms reliability. But the problem with alternate forms reliability is that it is often really difficult to come up with one good form of an assessment, much less two forms, two completely independent, equivalent forms. So, because of that difficulty, you can see how the reliability coefficients can be both high and low depending on the quality of the two types of tests that are created. So alternate forms reliability can be spuriously high or spuriously low depending on the quality of the test that you're using, the alternate form. We also have internal consistency, which relates to the consistency of responses within the test itself. So internal consistency can be measured through split half reliability with items that are split into two halves. So this test is administered at once. You have participants take one full test, and what you do is you take the test and you split it into two halves, and then you test for the internal consistency or the reliability from the one half of the test to the other half of the test. Oftentimes, when you are developing an assessment, there's a sense of like maturation or time components that can come into play with other types of reliability. And with an internal consistency, you're able to eliminate those because you're not asking people to come back a second time, and you're also not asking them to change over time. Like they're not aging. They are taking the assessment at one time, which can be a benefit to internal consistency. Oftentimes, as you are doing an assessment, your assessments get more difficult as you go through the assessment. So, if that is true for an assessment, the way that you break an assessment into two halves is by going like all even numbers and all odd numbers, and that's the two halves that you create. Split half reliability is sometimes thought of as like a special type of alternate forms reliability, but split half reliability is often corrected by the Spearman Brown formula because it can account for the decreased number of items that are being used to determine your split half reliability because you're splitting your test in half. So When you're using split half reliability, you really have to account for the fact that you are taking an entire assessment and splitting it entirely in half. So each of your assessment measures is half the length that you would expect. And the Spearman Brown formula is a way to account for that split so that you can get a reliable reliability coefficient that takes into account the decreased number of items. The second type of internal consistency that we talk about is inter-item consistency. And inter-item consistency assesses the extent to which any of the items on a test are related to each other, and then how those items relate to the test as a whole. So each item in a test is correlated with the total score for a client and then compared to the overall variability of scores within the test. So essentially, inter-item consistency is the correlation of all split half reliabilities. We oftentimes measure inter-item consistency through the Kruger-Richardson Formula 20 or the KR20 or Cronbach's alpha or some efficient coefficient alpha. So then the final type of reliability that I want to introduce to y'all is inter-rater reliability, which is the degree of agreement between two or more independent judges or raters. So inter-rater agreement is calculated by dividing the number of agreements that an event occurred by the number of possible agreements. So you're looking at the number of agreements and the number of disagreements, and you are relating them to one another to create reliability. So the way that inter-item reliability or inter-rater reliability works is you have two judges that are looking at the exact same behavior or the same output, and you are comparing how often they agree that a behavior occurred or that something occurred and how often they disagree. And you divide those two from one another to determine the reliability between them. The problem of inter-rater or inter-scorer reliability often comes into the fact that when you have two independent judges, they're human people. They are going to make subjective judgments that are involved in how they score each item. And even the most well-trained raters with the best instructions are still going to vary substantially in the ratings that they give to any observations that they have, which can then change reliability coefficients. So when you have that, you might see some spuriously high or spuriously low inter-rater reliabilities depending on the quality of instruction, because we're human and we're going to vary from one another, even if we are well trained. So that's going to wrap up our conversation on the first half of Chapter 5. Join me all for the second half of Chapter 5, and I will see you all in the next lecture.